So in this section, 8.3, we are not learning a new method of integration like we did in the last section. Integration by parts is definitely a new method that you have to practice, and it's different than U substitution, which is our other method. In section 8.3, we're not learning anything new per se. What I'm actually doing here is I am going to be mostly using the method of U substitution. Sometimes I will use integration by parts, but I want you to look at this first page not being horrified by all of these expressions that you see, but more of this is kind of like a flow chart for you. This is, depending on what you see in your integrand, what you should be doing to get your U substitution nailed down on the first try. When you have, complicated trig functions put together, sometimes it might be confusing what you would let U equal in a basic U substitution. So I'm just going to kind of put that up top here, that we're really using the method of U substitution for most of what's going on. We're just going to make a really good choice of U, and these are the strategies to help you do that. There is one little moment that I'm going to fly down to. Let's see if I can find it. Right here, where we might be using integration by parts periodically. It doesn't happen often, but it's worth noting. Okay, so this is not a new style of integration. This isn't anything new to learn per se. It's just getting you to be more efficient with using and choosing a good U for a U substitution. So if I just talk out a couple of these, and we're gonna go through a bunch of examples to explain them in more detail. I tend to teach by example, but if we just think about what this statement is saying, if you have an integrand and the power of the sign is odd and positive, we're always going to think about the powers being positive. You're going to save one sign factor, and any other you're going to convert to cosines. We're going to do this using some trig identities. So let me just be clear about what's happening in this particular case. What you're going for here, and maybe I'll just change the color so it stands out, you're going for a U substitution where you let U equal cosine. You're going to save one sign factor. Now the reason you're going to save that one measly sign factor is because if you convert this over into letting U equal cosine, like that's going to be our U substitution strategy, well then I know I have a follow through and its derivative involves the sine function. So by you saving that one sine factor, you see where this train is headed here, that you actually need that guy to cancel out the dx swap. So if I can just sort of make it more obnoxious in your face here, that like that one little sine factor that you're leaving off to the side is going to be able to be canceled with this sine x in your follow through. So your integral is going to be a bunch of u's and then a du. The sine is going to cancel with that one little guy that you leave off by its side. Okay, it's going to be very efficient at working this out. If you read through number 2, if the power of cosine is odd and positive, guess what? We're going to save one cosine factor, and we're going to convert the remaining factors to sines. So right there, that tells you in this case, we're going to do a U substitution, but we're going to let U in this case be sine, and we're going to save that one cosine factor because when we do our follow through, you get a cosine of x that comes out. So we're really using the method of U substitution. We're just being very efficient at choosing the best U to get the answer quickly. All right, now if I take a look at option 3 in our flow chart, this is just a Pythagorean. This is not a Pythagorean. This is just a trigonometric identity here. This is called the power reducing identities, that you can actually take sine squared and reduce it down to this statement here. Okay, so these are your two power reducing identities. They're from pre-calculus. They're rarely used, right? But we're going to definitely use them here. So let me be clear about how this identity works, because it tends to confuse people. So I'm just going to talk it out here. Sine squared of x is 1 minus cosine of twice x over 2. So let me explain. So what this means is, maybe I'll put like an arrow. This implies, okay, what if we were trying to reduce this expression? Let's just talk this out for a second. I'd be using the first guy, right? And so what this would look like is it would look like this. I'm not going to put a 2x here. I'm going to put twice what that angle is, and twice that angle is 16x. And let's just take a minute and think about, like, why would I want to do that? I mean, I can't, there is no basic integration structure for sine squared, but if I think about what I have going here, if I just kind of break this up, right? This is a really efficient way of knocking down that power on sine, and you're legally equating it to this expression here. You can integrate this pretty quickly. Okay, so there's different strategies of handling different trig functions, and this section is really just focusing on trig functions in and of themselves and making good choices. I'm going to come down here to the secants and tangents. They work the same way in terms of why are they telling you to do what they're telling you. So let's come at it from here. If the power of secant is even and positive, we're going to save a secant squared factor. You're going to leave secant squared all by itself. You're doing that on purpose because you're going to convert the remaining stuff to tangents. What that tells me is, in this case, again, we're using a basic u substitution, but in here, we're going to let u equal tangent. And the reason we saved that secant squared factor is because, well, that's the derivative of tangent. So again, I want this u substitution to work out amazingly perfect, and these are the strategies to do that. You see the same thing here in option 2. If you happen to have the tangent power odd and positive, we're going to save a secant tangent factor and convert everything over to secant. So you're going to let u equal secant. And the reason you save that one secant tangent factor is because the follow-through is that. The derivative of secant is secant tangent. Okay, so you're trying to maximize your skills with u substitution. Okay, and so we'll handle some of these other ones as we go. We're just trying to like work out what the best choice of u is and kind of like predict that follow through. What's gonna give you the biggest bang for your buck here moving forward. In the bottom here, these are other pretty advanced trigonometric identities that you probably have not seen since pre-calculus, and 0 people probably remember them. So we will definitely execute these when we actually have an integral. So the whole point here is trying to be able to come up with you're going to be asked to do the integral of this side. And you can actually kind of equate it to what you have over here. And the integral on this side is actually going to be easier or doable, let's say, than what you have on the left. All right, so trig identities, everyone's favorite. Let me talk about the ones that you need to know and that you need to use and use pretty quickly, pretty efficiently here. So let's go with them. The ones you can never forget, no matter what, are your Pythagorean identities. Okay, so that is this. That's sine squared plus cosine squared equals 1. That's from the unit circle. Okay, and keep in mind that with all of these identities, let's sort of mention it here, that's a true statement. You can wiggle these around and rearrange them if you want to, right? So if sine squared plus cosine squared is 1, well, then that means I could actually say, well, isn't it true that sine squared is 1 minus cosine squared? That's absolutely true. Isn't it true that cosine squared is 1 minus sine squared? That's absolutely true. You can wiggle this statement around and move and shake things together and come up with new true equality statements. So an identity is true no matter what angle you put in, so you can kind of morph those around. Now, your two other Pythagorean identities are tangent squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. Okay, so again, these are all your Pythagorean identities. You can change them around however you see fit. You know, if you really wanted to, like, couldn't you say tan squared is secant squared minus 1? Of course you can. Okay, so you can maneuver these around however they suit your needs. And this sort of kind of is the extension of the front page there. Like, how do we convert to cosines, or how do we convert to tangents, or whatever? We're going to use these identities a lot. So other identities that you should know off the top of your head without too much trouble is you want to know the reciprocal identities, which most people do know. You guys are pretty good, I think, at remembering those statements. That 1 over sine is cosecant. Of course, 1 over cosecant equals sine, and you can handle that in any way that you want to. That 1 over secant is cosine, and so that means 1 over cosine would also be secant. And then your other identities here, of course, well, I guess finishing out the reciprocals, 1 over tangent is cotangent, and 1 over cotangent is tangent. Okay. There's also your quotient identities. I'll switch colors for that one too. What are your quotient identities? Quotient identities are that tangent is sine over cosine, and that cotangent is just the flip of that, cosine over sine. We discussed that in Unit 1 as far as those basic trig ratios go. Okay, but they are identities that you should know. So let's talk about a couple of trig integrals that you should already know, or that are defined for us. And there might be some new ones, but definitely the ones that we've been working with for a while now. Let's just kind of go here. I know you know the integral of sine, and that's negative cosine. Again, these are all things that you already know. So when you have just these, standalone trig functions, you know this. You know the integral of cosine is positive sine. You know the integral of secant squared, I hope, is tangent. That's because secant squared is the derivative of tangent. So think about that relationship between what's happening with an integral, right? So if I just kind of remind you, remember, the integral of f prime is f. So a lot of times it's helpful to think about it this way, like that integrand, say, what? That's the derivative of some function. What is the derivative? What is that the derivative of? And then you can find your answer. So it's often helpful to think about your integral work that way. All right, so I'm going to come back over here and kind of work on those. Another one that I could do would be secant tangent. That should be an easy one because that is the derivative of secant. These are all things, hopefully, that you already have memorized. And these might be weaved into the more complicated trig integrals. So again, you always want to make sure that you are reviewing your basic integration rules and structures before you think of doing anything more advanced. Okay, so kind of finishing out some of these basic trig rules, just based on derivatives. The integral of cosecant squared is negative cotangent. That's because the derivative of cotangent is negative cosecant squared. So they kind of go together. And then here's your last basic one. If you come against the integral cosecant cotangent, no powers here, right? Let me put the dx in there. Then this would be negative cosecant. Okay, so those are a lot of your basic integration rules that you should be able to just kind of roll off the top of your head. There's 4 more that you may have memorized at some point. They might be new. So let's just go for it. What about just tangent alone? Just tangent alone. I'll actually prove this one to you. There's actually 2 answers to this. So let's sort of talk about it. Here's your rule. I'm just going to put it in terms of like having a rule for it. It's negative natural log absolute value of cosine. Or you could write positive natural log absolute value secant. Either one are fine. They're perfectly equivalent to each other. And maybe it's worth some time to think about that. So let me prove just that one. Maybe, here, I'll do it in a dark purple. Okay, let's kind of think of how this works. If I'm going to prove this to you, what I'm going to do is reimagine the tangent. So I'm going to use that quotient identity, right? So the tangent is really sine over cosine. I'm going to try to, let's see if I can move this over. I'm just reimagining tangent and rewriting that integrand into something equivalent, right? I know that tangent is sine over cosine. You can legally make this swap. And so from here, let's use a basic U substitution. I'm going to prove that this is what the integral works out to be. And I'm going to do that not by doing anything terribly fancy. I'm going to do that by doing a basic U substitution. I'm going to let U equal cosine. I'm really going for that log rule, that 1 over U du. So whenever I do a U substitution, there's always a follow through. And I'm going to go ahead and work on this. What I have here is the integral. I didn't really worry about the sine function in that numerator. What I did do is I let the whole entire denominator be U. And in place of dx, I have to write its equivalent, which is du over negative sine x. And this is good enough to work for me, right? Because the sine up here cancels with the sine down there. I do have a negative sign hanging out, but that's okay. You have accomplished your goal of really getting this to work out. This is 1 over u du. I'm going to squeak that negative in there, which the antiderivative is negative absolute value of u plus c. And you see where this is going here. You let u equal cosine, and so that's the rule that you see, right? There it is. It's right there. And then if you think about all of those rules of logarithms, let's see, how do you get from the first expression to the second expression? These are equal statements. What I'm going to do is come in here and really work on this negative. I'm going to say that negative is like -1. It's -1 multiplying that natural log. Okay, so that's great. What I can do with a log is I can put that power on the inside of the logarithm. And so that means what you have inside that logarithm is 1 over cosine, which using that reciprocal identity is secant. So you can kind of see how all these things work together, and now you see how I get that second equivalency. Okay, so sometimes it's just a little crafty use of U substitution that you could prove these things out. And if you forget what the rule is, you could certainly prove it this way. But I'm going to come over here and I'm going to put the last 3 integration rules that we should know and be able to do. So if we can do tangent alone, similarly, we could do cotangent alone. And this would be your final answer there. There is no alternate. This is it. Okay, and then more complicated, but we can do it. These are just standard rules that you can apply. The integral of cosecant alone, no power, is negative natural log, and this is a mouthful in here, cosecant plus cotangent inside that natural logarithm. The last one here is secant, which is also a natural log, and that's secant plus tangent. Okay, so this is everything that you currently know right now about trig integration. And so this section is really pausing for this one moment and talking about trig in and of itself and trying to be the most efficient. U substitution is interesting because you can try lots of things and some might work and some might not. This section is designed to give you the best possible move forward, the correct U substitution on the first try. Okay, so we'll definitely be using these. I'm going to do a lot of examples and show you by example on how to use that flow chart on the first page of our notes for this lesson.